I am Anil Kumar. Welcome to my series on polar equations and curves. In part 1, we discussed about the basics and now we are going to extend. In case you want to learn from me, you can always send an email on the address given. Also, check our website for the new videos being uploaded. As I said, we're looking into polar coordinates extended in this particular video. I'm going to talk about the polar equations and curves. Part 1 is the type of curves which we are going to draw by converting the polar equation into Cartesian equations. Then we look into polar equations and symmetry. There are three kinds of symmetries which we'll discuss. Once we know the symmetry, then we can actually have table of values for the restricted portion, and using symmetry we can actually sketch the curve. Well, the polar curves will also have restrictions, so we'll look into examples where the restrictions will be applied. So all these examples which I am discussing in this particular video are from previous test questions. Here are a few examples shown here of the polar curves. We are going to look into these one as we move along. Let's look into the examples which we covered in part 1. So earlier, when we were talking about polar Cartesian relations, we discussed that the relation is that x is equals to r cos theta, y is r sin theta, x square y square is r square, and tan theta is y over x. What I'm trying to say here is something like this. When we talk about the polar coordinate system, let's say this is the point P given to us whose coordinates are r and theta. That really means that r is the distance from the pole, which I'm writing O here, and the angle with the horizontal axis is theta, right? So this axis called the polar axis. Sometimes we also write it with letter L, right? So this is polar axis. We may write letter L for this particular axis. It's a ray originating at the origin, moving rightwards. And the angle, which are counterclockwise, are considered to be positive. We saw that if I drop a perpendicular from here, then putting this on a coordinate plane, y equals to r sine theta and x is equals to r cos theta. Since this is a right angle triangle, gives you the connection between the polar and the Cartesian coordinate systems, right? So that is what is the background. In part 1, we also discussed how to sketch the graphs. Some of the curves which we have drawn in part 1 are given here. So these equations which we covered in part 1, if you really want to understand how did we do them, you can actually look into the uh, link which connects to the part 1 of this particular video, right? Okay, now let's begin with extension to part 1. So first thing, we'll again take up some equations. The question here, which I'm saying is example 1, is again looking into equation of a line. Now this line is not a direct variation. It does not go through the origin, right? So it has some other y-intercept. The question here is, show that the equation r equals to 5 over 3 cos theta plus 4 sin theta can be written as ax plus by plus c, right? A form of equation. Find the values of a, b, and c, and then you need to sketch the graph. So these are the three things which you have to do in this particular example. We'll begin by the very first thing, which is r is equals to 5 over 3 cos theta plus 4 sin theta. So to convert that into Cartesian form, we can cross multiply, right? So the first step which we like to do is cross multiply. So when you cross multiply, you get r times 3 cos theta plus 4 sin theta equals to 5. Open the bracket. 3r cos theta plus 4r sin theta equals to 5. And now you can substitute r cos theta with x and r sin theta with y, just as shown here. That is the relation, correct? So what do you get? you get equation of the line. You get the idea. So this is the equation of the line. And comparing the coefficients, you can find the value of A, B, and C. Here is the graph of the given equation, which is r equals to 5 over 3 cos theta plus 4 sine theta. Do you see that? And now look into this and try to correlate. The equation which you got was 3x plus 4y equals to 5. Do you see how the connection is? So this 3 is there, you go, right? And then this 5 is the number right there. And the coefficient of sine is the coefficient of y. And that is how the equations are related. So I hope that really helps. Perfect. It's a good idea to write down all the equations and make a table with their graphs on the outside in the other column. Okay, now let's take up the next example, which is again an equation of the line. The question for you here is, show that the equation, which this time is r equals to 3 cosecant pi by 4 minus theta, represents a straight line. Then you sketch the curve just as we did last time. Perfect. Now some of you might know this compound angle formula, which will be applied in this particular case to simplify the equation and write it in the Cartesian form. Sine A plus B, as you know, is sine A cos B plus cos A sine B, right? So cosecant is reciprocal of sine, right? So we have written the equation r equals to 3 cosecant pi by 4 minus theta. Cross multiply, so we get r times sine pi by 4 minus theta equals to 3. And now expand this using the relation, which is right there. So you get what? You get sine pi by 4 cos theta minus cos pi by 4 sine theta. So if this is minus here, right? If it is a minus b, then in the center we have minus, and that formula is being applied here. Now we can just expand and simplify. So once you expand, you get the term r cos theta, and you know what r cos theta is, right? So you know r cos theta is x and r sine theta is y. Substitute x and y for r cos theta and r sine theta to get the equation of the line. I've written this in slope intercept form, y equals to x minus 3 square root 2. Perfect. And here is the graph of the line as shown to you. Correct? So that is how the line could be sketched. So I hope that makes sense. Now here is the third example in which we are going to convert to Cartesian form to sketch the curves. Example 3. Equation of translated circle. Show that the curve r equals to 2b sine theta is a circle with radius a. Radius should be b, right? Since we have 2b, with radius b centered at 0b. So in this case, we'll begin with the given equation, which is r equals to 2b sine theta. We'll multiply by r on both the sides. The idea is to get the term r sine theta, which can be written as y, correct? So we get r square equals to 2br sine theta. Now, we know that r sine theta can be written as y for us, and therefore, we'll write y in this particular case. So r square is x square plus y square. So that has been replaced by x square plus y square. So the equation now becomes x square plus y square equals to 2by. Bring y to the left side with the negative sign. And now at this stage, we need to complete the squares, right? So now we complete the squares. By adding and subtracting b square. So add b square and subtract b square. That makes these three terms a perfect square. So now we get x square plus y minus b whole square. And taking this minus b square to the right side gives us equal to b square. What is that? That is an equation of a circle with radius b and the center at 0b. So there you go. We get this particular circle which has the center at B, right? And the radius also of B. Correct. So that is how you can sketch this particular graph. So I hope you understand this strategy. Now we look into a very good concept to sketch the graphs, and that is symmetry. Most of the polar equations will exhibit some kind of symmetry, right? In the previous example also, you can see that the graph is symmetric about theta equals to pi by 2, correct? The vertical line, right? So at this point, theta is pi by 2. So that is the kind of symmetry. Now, if I would have understood that this is symmetric about the theta equals to pi by 2, in that case, I would have drawn only one half of the graph and reflected the other half to get the complete graph. That saves time in examination, and that's a very critical thing to do, correct? And therefore, my suggestion here is that always look into symmetry. So when you begin sketching the graphs, especially the polar equations related, look into this symmetry first. Most of these graphs will have some kind of symmetry. Okay, so let's explore symmetry with the help of examples. Now, can you identify the symmetry shown in this particular graph? And then look into the other two. What kind of symmetry do you see? Well, in this particular graph, the very first one, this circle, you see the semicircle has been reflected on the polar axis. So clearly, the symmetry about the polar axis can be seen. Now, when I say polar axis, it really means that theta equals to 0, right? So that is the line about which it is symmetric, correct? So that is how we could actually look into the symmetry. So let me draw the line of symmetry in a different color. In the second graph, we see that theta equals to pi by 2 is the symmetry, right? So in this case, it is 0, right? In this case, it is pi by 2, where you see the symmetry, correct? So we have symmetric about the vertical line, theta equals to pi by 2 in the second case. Now in the third case, we see that the graph is diagonal. It is symmetric about the pole itself, and so this is symmetric about the pole, correct? So here, this is symmetric about the polar axis, and this is symmetric about the vertical axis, where theta equals to pi by 2, and this is symmetric about the pole. Clear? So these are three very critical symmetries to analyze before sketching the graph. Now, once you know about these symmetries, let us explore how do we figure it out. Well, from the graph it is clear, but most of the time you are sketching a graph from the equation. So when we talk about the equation, clearly, if we have a point which is P r theta is same as P of r minus theta, that means we have a point here and then we have a symmetric point here, right? So those points which I'm showing here are symmetrically placed, correct? So if we have theta and we have a similar point here, which is for minus theta, in that case, we definitely have a symmetry about the polar axis. So that becomes the condition. It really means that I could always write the equation as f of minus theta equals to f of theta. Since the r value remains same, do you see that? The r value remains same. So f of minus theta equals to f theta is a way to test the symmetry about the polar axis. Example you can see is like r equals to a cos theta, right? That is what we did earlier in our part 1, correct? Now here we see a symmetry about the vertical, which is theta equals to pi by 2. The point PR theta can now be written as same as PR pi minus theta. What we're trying to say here is something like this. If you look for a point here on this axis, so let's say this is the point P, making an angle, in this case as shown here, pi by 4. In that case, we can say that there's another point which is right there, symmetrically placed, right? So let me write this as P and this as P dash. Now, what do you notice here? That these two angles, if this is theta, then that angle should be pi minus theta. If that is the case, we have the same r value. Do you see that? We have the same r value. In that case, we have symmetry about the vertical line theta equals to pi by 2. You can always test this for the function f of pi minus theta equals to f of theta. Perfect. Now, example is what just we did. R equals to 2b sine theta. Perfect. The last one here shows a symmetry about the pole itself. So these points which we have here, they are symmetrically placed. That means that this value is r, this is minus r, right? So basically means the angle is theta, right? The other angle here will be what? Pi plus theta. So we can say that if f of pi plus theta is minus f theta, in that case it is symmetric about the pole. You get the idea, right? So we have understood three kinds of symmetries. One for which f of minus theta is equal to f of theta. Then we have another symmetry where we have f of pi minus theta equals to f of theta. And the third one where we have f of pi plus theta equals to f of minus f of theta. Correct. So these are the three symmetries which we can look into and then sketch. We'll take up two examples now to show you how we can just make a table with few values and get the complete graph. Okay. So that is kind of important to understand. Let's take up the example, which is example 4 for us. We will explore the symmetry and then sketch the curve. The question for you is to sketch the curve for the equation r equals to 4 cos 2 theta, right? So that is the equation for you, r equals to 4 cos 2 theta. So in the first part, we will see how to test for the symmetry. Well, writing f theta for r is the very first step. It helps us to provide a simple explanation, right? So the equation has been now written as f of theta equals to 4 cos 2 theta. What is f of minus theta? Replace theta with minus theta. When you open this up, cos of minus theta is cos theta, right? You know that. Cos is an even function. So we know cos of minus theta is equals to cos theta. And therefore, we get the result as f theta. That means it is symmetric about the polar axis. So we got the first symmetry. It is symmetric about the polar axis. So that means if I'm going to sketch, this is my polar axis, right? So it is symmetric about the polar axis. Now, let us check the second symmetry, which is about the vertical theta equals to pi by 2. In that case, we'll check for f of pi minus theta. If I substitute pi minus theta for theta, then what do I get? I get cos of 2 pi minus 2 theta. Now 2 pi is the period, right? And therefore, that should be equal to cos of 2 theta, right? So this is equals to 4 cos of 2 theta, which is same as f of theta. And therefore, it is also symmetric about the vertical lines. It is also symmetric about this line. So we have found that it is symmetric about these two lines. Now, let us also test for the third symmetry, which is about the pole. So f of theta plus pi will be what? When you multiply by 2, you get 2 pi plus 2 theta. Since the period is 2 pi, it is same as equals to 4 of cos 2 theta. So that is f of theta. So it is symmetric about the pole also. It has all the three symmetries, right? All three symmetries. Now that is important. So what you could do is you could only check for the points in quadrant 1, for example, between 0 to pi by 2, right? So we can talk about 0 to pi by 2, and then once we have these points, we can reflect these points about the horizontal, which is the polar axis, about the vertical, which is theta equals to pi, and about the pole to get the complete graph. You get the idea, correct? So what we are doing is now make a table of values. So in this, we have taken the value of theta as 0, pi by 6, pi by 4, pi by 3, and pi by 2. So we are only checking for these 5 values. Substituting these values into the function itself, which is for us 4 cos 2 theta, right? So when you substitute 4 cos 2 theta, when theta is 0, you get the value 4. When theta is pi by 6, you get 2. Then pi by 4, you get 0. Minus 1 for pi by 3. and for pi by 2 you get minus 2 as your answer. Now you have these points to be plotted. Let me just plot these points on the graph. So the first point is 0, 4. So when angle is 0, theta is 0, then r is 4, correct? So that becomes your first point. At pi by 6, you have a point which is 2. So that gives you the second point. At pi by 4, the value is 0, which is the origin. And at pi by 3, we have minus 1. So at pi by 3, we have a point which is minus 1. And at pi by 2, we get a point which is minus 2. So that helps you to get the points on the curve. Now you can join these points to make a perfect curve. Do you see that? So we have a portion of this curve. Now we know that it is symmetric about the polar axis. Polar axis really means that it is symmetric about this horizontal axis. You get the idea. So now what we should do here is we can reflect the portion on the horizontal polar axis. Reflecting this part, we get the part here, and now reflecting the other part, we get the other part right there. Do you see that? So that is what we get. Now, that is the reflection we have done about the polar axis. Now, we also know it is symmetric about the vertical axis, and therefore we are going to reflect it on the vertical axis. So I get this portion here also reflecting about the vertical axis. We get that portion, right? So we get this portion reflecting about the vertical axis, and these two lobes which you see can now be reflected, and we complete a flower. So we have a flower here using these two symmetries. Well, what you notice here is that if a curve is symmetric about the vertical theta equals to pi by 2 and the horizontal polar axis, then it is also symmetric about the origin, correct? So this is implied, right? That implies the third symmetry. And what you get is the complete graph. Do you see the beauty? So from the table of values of just 5 points, we are able to sketch the graph of r equals to 4 cos 2 theta. Does it make sense to you? Perfect. That is how you could actually sketch it. You can actually pause the video, look at it carefully, understand, and then move forward. Now here is the last example. I would like you to pause the video. Take this as your test question, correct? So treat this as your test question. We need to sketch the curve for the equation r equals to 2 over 1 minus cos theta, where theta is between 0 and 2 pi. Okay, to begin with, since we have something in the denominator, intuitively you should check for restrictions. So we have an equation which I've written in f theta form, right? It is a function of theta. Now, the restriction here is that the denominator cannot be equal to 0. Clearly, that gives you that theta is not equal to 0 and 2 pi. Well, that is why in the domain we have given theta greater than 0 and greater than 2 pi. Sometimes that may not be given to you. In that case, it is a very important information to be included in this solution, right? So look for restrictions. Now let's begin with checking the symmetries. So let's find what is f of minus theta. F of minus theta, you know, cos of minus theta is equal to cos theta. So we know we should try for that symmetry, right? And it is equals to f of theta. That means it is symmetric about the polar axis, which is shown here. So it is symmetric about the polar axis. Now, once we know it is symmetric about the polar axis, we can actually check for the points only from 0 to pi and then get the other points. You get the idea, right? You can also test for the other symmetries, right? So I'll just write test for other symmetries. Okay, it is important to test. In our case, I have not done this testing since I knew kind of, right? So but for you, you have to test for which all symmetries does it belong to, right? So replace theta with pi minus theta and check, do you get the same value of f of theta or not? Okay, since we found that it is symmetric about the polar axis, instead of 0 to 2 pi, I'm only checking the values from 0 to pi. So again, I have these values from 0 to pi, which I'm going to check. Of course, when I substitute 0, I get does not exist, a very, very large number. So at 0, we do not really have any particular point here, correct? But for pi by 6, we get a value, 14.9. Substitute the value in the given expression, right? Which is 2 over 1 minus cos theta, right? So remember this. We're trying to write r equals to 2 over 1 minus cos theta. Substitute and then write down your values. So you get 14.9 for pi by 6. For pi by 4, you get 6.82. Pi by 3 is 4. Pi by 2 is 2. 2 pi by 3 is 1.3. 2 pi by 6 is 1.07. And for pi is 1. So these are the values which I got. Well, let me show you. We'll start from the last value here, which for pi I got the value 1. 5 pi by 6. I'm getting 1.07, slightly bigger, so that is my 5 pi by 6. And then 1.3 for 2 pi by 3, which is right there. And then for pi by 2, it is 2, correct? So we are plotting these points one by one, and then we get the curve here. So those are few points which I could show to you. Connect these points with the line, and then you get one half of the curve, correct? And now from the symmetry, you can get the other part, right? From symmetry. See how easy it becomes. So from symmetry, we get the other half of the curve. And that is how you're going to sketch it. Perfect. So you get your curve, which is shown here. I hope it makes sense. Feel free to write your comments, share your views, and if you like and subscribe to my videos, that will be great. And if you have any questions, feel free to post them. Thank you for your time and all the best.